For this optimization problem, they're asking us to maximize this quantity, this weird quantity 2xy squared, if we have the constraint, or if we have the condition that has to be met, that x plus y squared equals 1. All right, now let's just think about what this is asking first, and then we'll try to solve it. So they're asking us to find a certain x and y pair, ordered pair, that when we plug it in here, 2xy squared, t will be as big as possible. Now, if that's all that was said, we'd say, well, okay, just pick a giant x and a giant y and plug them in, and we'll get a giant value for t. 2 times 1,000 times 10,000 squared, or something along those lines, and we'll get a really big t value. Well, we also have this constraint that has to be considered as well, that x plus y squared can't be anything other than 1. And so that really limits your options. So this guy right here is called the constraint. That's what has to be met. And this guy here that we're trying to maximize or minimize is called the objective function. The objective function. So normally all these optimization problems have an objective function, and they have a constraint that has to be met. All right, now there's another problem as well. All right, look at this t here. All right, even if you just wanted to focus on the idea of maximizing t, we're very good using calculus at maximizing or finding the maximums of functions. If this is a graph of t right here, then I know all I need to do to find the maximum using calculus is take the derivative and set it equal to 0, and all those good things. Well, there's something subtle that's another problem with this function here. So here's another issue we have going on here. If this is t, this assumes that t is only a function of one variable. You see, looking at this graph, this is a two-dimensional graph. That means one input, one output, like x and y. Well, here we have x's, y's, and t's. So due to the fact that we have two independent variables, that creates some issues as well. Well, it turns out this constraint is actually going to help us. People often think of this constraint as something that makes the problem harder. It actually makes it a lot easier for us, because what the constraint will do, it will allow us to reduce the number of variables from 3 total down to just 2. And then we can proceed with our calculus and whatnot. So here we go. So we've got t equals, all right, currently 2xy squared, 2xy squared. That is too many variables. This objective function has too many variables. So now, look at this constraint right here. Any thoughts as to how we could use this constraint to reduce down the number of variables we have on the right-hand side? We know that x plus y squared has to be 1. X plus y squared has to be 1. So doesn't that reveal, let me erase this here, doesn't that reveal the fact that x would be 1 minus y squared? You can solve for one of these variables. If you have a constraint that has like x and y, you can solve for one of them in terms of the other guy. Now again, maybe it's still not clear. All right, now how can we take this and reduce this number of variables from x and y down to only x or only y? Well, here we go. I'll make it very clear now. If we have 2xy squared and this is x, if x is 1 minus y squared, then you can do a little copy and paste. You can take this x out and replace it with a 1 minus y squared. So let's look here. Let's rewrite t. So instead of being 2xy squared, 2xy squared, I know what x is due to the constraint. It's 1 minus y squared. So we can write t equals, let's see, distribute that 2y squared through the binomial. You get 2y squared times 1 minus 2y to the 4th, which is 2y squared times y squared. And this is better. This is better. Why? Because now that t is only in terms of y solely. So now we can go ahead with this type of idea of taking a derivative and setting it equal to 0 and that sort of thing. So let's do that. So what would t prime be? That would be 4y, right? 4y minus 8y cubed, 4y minus 8y cubed. And then if we want to set this equal to 0, trying to find a critical value, we have a common factor of 4y. So we'll pull a 4y out. We'll have 1 minus 2y squared, it looks like. 1 minus 2y squared equals 0. So either this is 0 or that's 0. If you have a product equal to 0, one of the two has to be 0. So if 4y equals 0, that would lead to y being 0. Good. If 1 minus 2y squared equals 0, then after some algebra, I'm going to speed things along here, y would be plus or minus the square root of 2 over 2. Typo, sorry about that. Square root of 2 over 2. I did skip a few algebra steps there, so you might have to do that on your scratch paper, but this is the y values you would get. Now, that shows that we have 3 critical values. Now, we don't know if these are maxes or mins, or we don't really know what they are. So at the end, we really need to go back and actually plug these guys in to see if they actually create maximums or minimums, in fact. So you can create a couple different pairs here. Let's see here. We had y being 0, we had y being root 2 over 2, and we had y being negative root 2 over 2. Now that's just the y's. How do we get the x's that complement those? Well, this is where, again, that constraint comes back in. If you recall, we know how x and y are interrelated to one another. So if y was 0, then the x would be 1. Okay. If the y is root 2 over 2 or negative root 2 over 2, since we're squaring it, it'll be the same thing. So let's think about that one. Let's see, 1 minus root 2 over 2 quantity squared. This would be 1 minus 2 over 4, right? Root 2 squared is 2. 2 squared is 4. And 1 minus a half is a half. So both of these, the x-coordinate would be a half. Okay, very good. Now, we don't know. All 3 of these are question marks. Maybe we have a maximum or a minimum, or, we're not really sure. So final step, how do we figure out which of those maximized t versus which one of those minimized t? So all we need to do is take this t, which was 2xy squared, and pop them in and just see, see who's the biggest and who's the smallest. Here we go, 2xy squared. Let's see what each of these would yield. Let's see, notation-wise, let's see, it would probably be easiest just to say t of xy, t of xy, and t of xy. And I'll move this guy down here for a minute. Okay, let's see, do a little algebra. If x is 1 and y is 0, this would yield 0. If x was a half and y was root 2 over 2, after some algebra, you would see that this would be a half. And if x was a half and y was negative root 2 over 2, do some algebra, you would see that this would be a half. And all I did was I took these x, y coordinates and plugged them in. So what do we see? Well, it looks like these two guys right here is where we found our maximums. So it turns out we had 2 places that achieved a maximum at 1/2 comma root 2 over 2 and 1/2 comma negative root 2 over 2. Now, just in closing, just to go back and summarize this, I just want to illustrate just how typical this example is for all optimization problems. It doesn't matter if you have a pasture adjacent to a river, like that typical example. It doesn't matter if you've got a cardboard box where you're trying to find the maximum volume. Every optimization problem starts off with an objective function that has too many variables. That's the constant thing for all these problems. But what always comes to save the day is the constraint. The constraint will always reduce the number of variables in the objective function down to just a single variable. And once you have your objective function as a function of just a single variable, then you can take derivatives, set it equal to 0 to find your critical values and all those good things. And then, from there, you can just use either basic calculus or basic algebra to figure out who's the maximum and who's the minimum out of those choices of critical values.